Hi, this is Mike Tochik. I'll be presenting today on electrical protection of insulated joints and all the issues that relate to that. Let's talk about insulated joints. What are these things? Basically, the functions of an insulated joint would be to prevent metallic contact between the two sides of the insulated joint. Therefore, this isolates electrically one side from the other, and cathodic protection is separated from one side to the other. The consequence of doing that is that the insulated joint has to withstand whatever voltage is presented across it, and that's where the complications come in for insulated joints. There are several types of insulated joints available, very different constructions. The first would be a monolithic or weld-in joint, where it's built to the diameter of the pipe that it will be placed into, and it's welded in place. It's a factory-built joint and has very good insulation and very consistent performance. A flanged isolation joint is one that is field assembled with bolts and flange face insulators, and I'll show an image of that next. Finally, a simpler and lower cost insulator for smaller connections would be an insulated union or an insulated fitting, such as would be in tubing. Here's the typical construction shown. In the upper left, we see a monolithic joint with a cutaway, and you can see a light yellow area that represents the insulation system between the left-hand and right-hand sides of this insulated joint. So this is clearly welded in place and is a permanent isolation feature. In the upper right, you see a flanged insulation kit, where the main insulator is the flange face insulator. It is sized for the diameter of the flange, and then every flange bolt has an insulated sleeve over it and an insulated washer. The bolt could be bonded to one side of the flange electrically by having an insulated washer on one side or the other. It could be insulated on both sides. If it's a buried flange, you'd have it connected only to one side so that the bolt is part of the cathodic protection system and receives protection also. Clearly, with this type of insulation system, there's a number of pieces and it has to be installed correctly. On the bottom, you see a small insulated fitting, such as what would be called a swedge lock fitting. And there's insulated members in there to separate the right and left halves, and it's a threaded connection, generally again for tubing, say 3/8 of an inch diameter. One type not shown would be an insulated union that could be in pipes of 1, 2, or 3 inches. So what is the capability of an insulated joint? Well, the voltage capability of the device is limited depending on the type of construction, the spacing, the thickness of the insulation. For unions and fittings, it tends to be lower values, perhaps hundreds or thousands of volts. These are rough numbers. For flange joints, this will relate a lot to the skill of the installer and not making mistakes, but if assembled correctly, it would be rated for thousands of volts. And monolithic joints for tens of thousands, perhaps 20-some thousand volts. So those are factory-made, very good insulation systems. The risks that relate to insulated joints, again, relate to voltage. If this insulating feature can allow a voltage difference across that joint, then that voltage is the risk. Voltage that was high enough could lead to arcing, and arcing again to insulation damage, steel damage. Finally, it could even ultimately mean product ignition if it's a flammable material inside the pipe. Here's what regulations say about insulated joints, at least for the US. So in Code 49 CFR 192, which governs natural gas interstate pipelines, it has this particular paragraph about an insulating device not being used where combustible atmospheres are present unless you take some kind of precautions to prevent arcing. And you'll notice the very general wording of this code. Well, here's a little bit of definition to help identify how you might sort out such a code. Insulated devices, it might be self-evident, but again, these are the insulated fittings, flanges, joints that we're talking about. Combustible atmospheres, in our case, would be gases, hazardous gases and vapors, but there has to be a little more definition yet on what type or how is it rated. You have to take some kind of precaution, but this code does not say what to do. But it does point towards preventing arcing. Here's the next paragraph of this code. It talks about pipelines near transmission towers and providing protection for fault current and lightning and dealing with insulating devices. So again, here's where insulators come into the story, and it's explaining that there's some kind of risk, but again, it's not well defined. Here, let's parse this a little bit further. It doesn't explain what equals close proximity, but clearly, if you're near enough to a transmission tower, there's obviously some bad things that can happen, they're implying. Protection has not been identified as to what you must do, but the risk has been named as fault current and lightning, and it doesn't explain again the protective measures, and we're assuming the same kind of insulating devices, say a flanged or monolithic joint in a cross-country pipeline. But this kind of general language really needs more definition. So we're going to spend some time talking about how do you address all of these concerns. How do we deal with and identify hazardous locations, teaching about AC and lightning hazards, and a little bit about static charge, but mainly about AC and lightning, and then what are the proper protective measures taken for overvoltage protection of insulated joints. So, about hazardous locations. If you're in the US, it is our National Electrical Code, or NFPA 70, that defines what is a hazardous location, and that happens in section 500 to 505. Now, other countries, Canada, for example, has its own codes, and other countries yet, similar codes identifying these hazardous areas. For us in the energy industry, we're talking about combustible gases and vapors. We're not talking about dust. That's another category. And the systems divide risks between low, high, or ordinary locations. So an ordinary location is where there's no release of combustible gases at any time. And then the classifications go up from there. Next would come a Class 1 referring to gases, Division 2, or alternately Zone 2, area, and that is the first level of risk. And that's generally true, or that site is present only if something were to fail, so an abnormal condition would exist. And a higher risk would be a Div 1 or Zone 1 area, where it's presumed that gases are often present or regularly present. In North America, it's very common to make reference to divisions, and typically elsewhere, the rest of the world will refer to zones. But just to confuse you, there are zone classifications within North America also as an alternative to the division system. Then further, there's gas groups. And the different gas groups relate to the flammability of the material inside the pipe. So in the division system, its gas groups run A, B, C, D, from highest to lowest flammability. And in the zone system, it does it just the opposite. So it's 2C all the way down through 2A. And this is just referring to the ignition risk of the material. Here's an example of graphically of what a hazardous area classification might look like, where the interior of a building might be considered a Div 2 area, or even more typically, it's generally Div 1. But you see the cross-hatched area where the trench and the pit and around the building and out to a 15-foot radius from a valve is all Div 2. And then around this gas release point, you'll see a closer cross-hatched area, and for a radius of out to 5 feet, that's a Div 1 area, surrounded by a Div 2 area out to 15 feet radius. And then surrounding all of that is an ordinary location, an unclassified area. And there's drawings like these in various documents to help a user understand how would you classify your site. Here's some photos of typical construction and typical sites. So for example, a Div 1 site at a tank farm where you're in the area or within the berm. This is a low depressed area. It's presumed to be a Div 1 site. gases could collect in this low area, creating an explosive environment. So here, this happens to be a jet fuel line. This was shown as a Div 1 area. The very same piping, though, on the outside of a building above grade might be a Div 2 area, and their protection of flanges here might only require a Div 2 product, not one rated for Div 1. There are additional documents that provide guidance to users on how you might classify your site. There's AGA documents for gas facilities or API for petroleum. I already mentioned the Code of Federal Regulations for the U.S., and that provides some guidance to users. And then the National Electric Code, or equivalent in other countries. An interesting link is that the generality in CFR 192 can be alleviated because it incorporates the National Electrical Code by reference. By just merely having the phrase included by reference, it takes all of the specificity of the National Electric Code and pulls it right into CFR 192. So that is how it defines what is a hazardous location and what is the risk, and what are acceptable products or wiring methods used in hazardous locations. So now you have some of the detail that tells you what to do. Now, not every code pulls in the National Electrical Code by reference, but clearly the risks are all the same, and the practices should be all the same because the risks are there. Now, when it comes to product construction to address hazardous locations, there's different types of construction for the different certifications. So, for example, Division 1 areas will typically require flame-proof construction. The magic phrase flame-proof is referring to the protection method. So this is where you'll typically see a cast aluminum box with a heavy cover and lots of bolts. The concept here with flame-proof protection methods is that it will contain the explosion and not allow it to propagate out through the threads or the cover fitting, things like that. That's compared to Div 2 construction, which is typically non-sparking. And so non-sparking as a protection method does not rely upon containing an explosion within and the overpressure within a housing. It instead never creates sparks or heat in the first place enough to allow an explosion. So very confusingly, both of these are explosion-proof, but they use different protection methods, and there's different construction allowed. And one needs to have a product certified appropriate for whatever is their classified hazardous area, for either the appropriate division or zone, and also for the right gas group. Here's images of typical protection products used on insulated joints or flanges. On the left, we see Division 1 construction, again a heavy cast aluminum box, and the product is connected across the insulated joint. And on the right, you see a fiberglass housed product. This is a Division 2 certified device used appropriately in its classified area. Let's now talk about what actually provides the overvoltage hazards to insulated joints. There are scenarios where there is common location of pipelines and power lines or other phenomena like lightning that can provide that overvoltage and cause an arc, the reason that we need overvoltage protection in the first place. So here's what insulated joints could see. They're subject to lightning generally at many locations around the US or around the world. Some pipelines and insulated joints are subject to induced AC voltage, and that would come where a pipeline is near a power line. And even further, if it's not right near a power line, many pipelines are still subject to AC faults. There are some applications that could be subject to static charge, such as liquid flow on pipelines, such as a fueling system. Here's an interesting map of the incidence of lightning around the world, and shows that some areas of the globe have very concentrated lightning activity, while other areas are almost devoid of lightning. Lightning has a very specific waveform, and it can be roughly categorized by standards, and here is an example of a lightning waveform, an 8 by 20 microsecond waveform, with a very fast rise time. That's the slope that you see of the rising waveform, up to some peak value, and then it has a decay down to a lower value. So when a waveform is described as an 8 by 20 microsecond waveform, and there's other waveform descriptions as well, what that means is that it has a rise time of 8 microseconds and a decay to half of the peak value after the peak of 20 microseconds. Lightning can do some interesting things to pipelines. It's very easy to flash over insulation systems with that fast rising waveform. Here's a photo of a flanged insulation kit where lightning has arced from the steel washer over the insulated washer to the flange face, to the outer flange face, more accurately. And again, the same thing, but multiple arcs established, where probably this would be easily cleaned up and repaired, but these arcing products are probably contaminated and they would track and allow current to flow. So this would need to be fixed if you were to have isolation. There's also AC hazards that can occur on pipes, and this requires a little bit of discussion. With steady-state induced AC, this is a hazard to personnel. There is a shock issue, but it probably is not going to result in an arc at an insulated joint. You do have to address it, and an AC mitigation is an entirely separate subject, worthy of multiple presentations. But we'll just mention it here and say that pipeline voltages can be mitigated. We aren't as concerned about the steady state for an insulated joint withstanding it, but the steady state does give rise or point towards the risk of an AC fault. Anytime there's AC induction, you absolutely have the risk of an AC fault level induction applying to the pipe. If there was an arc established in such a condition, again, it could arc across, damage the insulation. It could even damage the pipe and ignite products. So back in CFR 192, we did raise the issue that it has pointed out there are risks to pipelines where you are near AC facilities. We'll just talk for a moment about static charge. Again, there are liquid lines that can have static charge build up as the liquid flows through a system rapidly with low level, low energy arcing that can occur. It is an arc, it is high voltage, but it has very low current. And it does need protection in fueling systems against this, even though it's a very different energy level than an AC fault. Lack of protection has caused numerous incidents, and I outlined just a few of them here. But in several cases, just to point out, in the case of gas distribution, where a nearby AC fault affected a pipeline, it had unprotected fittings, insulators in sensing lines, gas fitting lines, and a resulting arc easily perforated the tubing, and it fed the fire that burned the facility to the ground. In the case of oxygen lines, there was an arc at an insulator, and there the oxygen and the steel were the fuel for the explosion and heavily damaged that pipeline. At a Florida compressor facility, a lightning arc at an insulator resulted in the entire facility burning down and was a complete loss. And another situation, not involving an insulator, but it is an interesting case of AC-induced fault current affecting a pipeline and then arcing to a road casing and then resulting in a fire. The ways that you deal with preventing arcing is to first know, is this a classified location? If it's classified, we want to use the appropriate classified product in that area to address the hazard. And further on best practices, we want to apply products, any protection product, with short conductor lengths to apply that product across the joint. The issue in a nutshell is the inductive effects that come from the very fast rising lightning waveform. This is only a lightning effect that produces this inductive kick. But the result is, the way you control this is to keep conductors to very short lengths, or more ideally, to use plated copper bus bars to support the protective product and to reduce that property of inductance so that the resulting voltage is lower. So here's an example of a monolithic joint, a welded joint, and a protective product has been mounted by the use of welded tabs on the pipe and up on the insulator, where that represents the two sides of the insulated system, and a protective product has been mounted very close to those tabs. So this would represent good practice. Might be a little difficult to see in this picture, but there's a gray box in front of an insulated joint. That protective device has been mounted on a mounting stand, and very short conductors have been used to locate that and connect it to the flange. Again, very good practice. Another method, very effective, would be to mount a product using bus bars right to the flange bolts and its mounting system. This is the product support, and it's the electrical conduction path. Here's a protective product that's been connected across multiple insulated fittings in gas measurement lines. So we see a series of 5 insulated fittings in 5 gas lines. They've been paralleled with cables across to a product so that all 5 of them have been protected. So here, good practice in not leaving out any insulated fittings. So in the end, to summarize, we want to use suitable products for protection. Products need to be certified for the area that they are placed in, so we use Div 1 devices for Div 1 areas, or Div 2 devices for Div 2 areas. The same applies if it was a zone system. Zone 2 products for Zone 2 areas, etc. In an ordinary location, there's not really a restriction. You don't have to use a classified device. Very commonly what happens is Div 2 or Zone 2 products are often used in ordinary locations, as that is the most efficient and lowest cost method. It still is a protected classified product, but it's used in the ordinary location for practicality. Make sure that devices have ratings for both lightning and AC fault current, as typically pipelines have this dual exposure. Many devices on the market are only rated for lightning. They are lightning arresters. If they were to see an AC fault event, they most likely would be damaged. Typical lightning ratings for products are somewhere in the range of 50 or maybe 75 to 100 kA as the peak value of lightning current. For AC fault current exposure, it's common to have products and exposures of several thousand amps. So this concludes our discussion about insulated joint protection. It's meant to be a primer on the basics of products, systems, and classifications. If there are more questions that come up, we're happy to address them. Thank you.